So Chips Ahoy cookies, the number of chocolate chips in an 18-ounce bag of Chips Ahoy chocolate chip cookies, it is approximately normally distributed with a mean of 1,262 chips and a standard deviation of 118 chips. And this was reported by the US Air Force Academy, or studied by them. So we want to find a set of probabilities using the information that is provided to us. So what we know is that the number of chips is normally distributed with mean 1262 and has a standard deviation of 118. So the first question is to find the probability that a randomly selected 18-ounce bag of Chips Ahoy contains between 1,000 and 1,400 chocolate chips inclusive. So what we want to find is the probability that X is between 1,000 and 1,400. Now, what is X? X is simply the number of chocolate chips in an 18-ounce bag. So we know that when it comes to normal distributions, whether we use a less than or equal to or less than, the answer would still be the same. There is no difference in whether I include the endpoints or put an equal sign or otherwise. So this would just be equal to probability 1,000 less than X less than 400. Okay, let me go back here. So we know that the mean is 1,262. And 118 chips is the standard deviation. So we can go one standard deviation to the left and about one standard deviation to the right. That sort of would give us an idea as to where the two endpoints would lie, which is 1,000 and 1,400. So I'm just guessing. So this would be 1,000 and that's 1,400. Mind you, these are lines that I'm guessing based on the empirical rule. It is not the exact value. And what we want to find is the probability. So we are looking at the area in between those two lines. So to do that, we are going to make use of the calculator. So just hide. Okay, so the function that we have to use is simply Normalcdf. So press second vars, number 2. The area starts at 1000, so we put 1000. It ends at 1400. The mean is given to us, which is 1262. And the standard deviation is 118. So if I put that all in, I will get a probability, but I always recommend that even before we try to get an answer using a calculator, if we think about it, the value 1000 is about slightly less than the first standard deviation on the left. On the right-hand side, it is slightly less than the first standard deviation. And we know 68% lies between the two standard deviations, one standard deviation to the left and one standard deviation to the right. So the answer is probably, 40 or 50%. Let's see if my guess is right. It's actually wrong. We are 86%. Maybe I did my math wrong somewhere. So it is 0.8657. Perhaps it's because we are really close to two standard deviations. That would only explain the answer of 86.57%. Moving on, part B. What is the probability that a randomly selected bag contains fewer than 1000 chocolate chips? So fewer would mean probability X less than 1000. And it is always a great idea to shade, because shading tells you where the area starts and where it ends. I strongly recommend it. So the mean is 1262, 1000 is somewhere over there. And now we want to find the area below. So that area would correspond to the probability that we are looking for. So we'll do the same, second vars, number 2. The area is starting at a lower endpoint of negative infinity. So negative infinity is on the left-hand side. So negative, second, comma, that brings up the E, 99, all the way up to 1000, which is where the area ends, right here. And the mean, 1262, the standard deviation, 118. And I get an answer of 0.01319, or you could write it as 1.319%. Oftentimes we prefer decimals. When we convey the message to the general public, we tend to use percentages, but more often than not, we like decimals. So part C would want to know the probability, in other words, the proportion. They use the word proportion, but proportion and probability are one and the same. So the key thing to note here is they are talking about the probability. So now the question becomes, what is the probability of 18-ounce bags of Chips Ahoy contains more than 1200 chocolate chips? So 1262 is over there. 1200 is very close to 1262. And since it is more than, we have to shade everything above. And we know the probability from 1262 and above is 50%. So whatever answer that we have to find has to be bigger than 50%. So probability of X greater than 1200. My guess, it's going to be over 50%, maybe I'm going to say 70% as a guess, about 70%. Let's see if I did okay. Second verse, number 2, we start at 1200 this time because the lower endpoint in this problem is 1200. The upper is positive infinity. In the previous one, the lower was negative infinity. The upper ended up being 1000. So the starting point is the lower value, so 1200. Upper is infinity, so second comma E99, which is E99. Mean is 1262, and the standard deviation is 118. Enter. 70. So I've redeemed myself. So 0.7004, or you could write it as 70.04%. So we want to find probability that X is less than 1125. All the troubles. So 1125 is somewhere over here, and we want to find the probability less than that. And just by looking at the area, we should get an idea that the value is going to be pretty small. So that's another indicator or predictor of what the answer is going to look like. So oftentimes in a problem like this, even before you start the problem, you should have an idea as to what the answer should look like. So second verse, number 2, we start at negative E99, end at 1125, mean is 1262, standard deviation is 118. And we get 0.1228. So part E, what is the percentile rank of an 18-ounce bag of chips Ahoy that contains 1,475 chocolate chips? So there is a key difference between the previous parts and this one. So if you read the problem carefully, they're not asking for the probability. They are talking about percentile rank. So where does a chosen bag of chocolate chips stand when we look at all the 18-ounce bags of chocolate chip cookie bags or Chips Ahoy bags? So where does it stand if we pick one bag and assuming that bag contains 1,475 chocolate chips? So even before we start the problem, we should have an idea as to what that percentile is going to look like. Now, 1,475 is definitely bigger than 1,262. So it's right over there. And it is certainly bigger than one standard deviation to the right of 1,262, because 1,262 plus 100 is 1,362. 1,362 plus 8 is 1,370, and 1,370 is the first standard deviation added to the mean, and it's going to be to the right of 1,262. And this value is certainly bigger than that number. So it's somewhere between the first and the second standard deviation. So I'm going to guess maybe the 90th percentile. This is just a guess. And also we could look at the area below. And we want to know what percentile rank that particular bag would stand at. So if I found the area below, that is going to give me the probability. So we need to find that area. Second bars, number 2, starts at negative E99, ends at 1,475, mean is 1,262, standard deviation is 118. So it's about 0.9644. So what does this imply? This implies 96.44% of the bags would contain less than 1,475 chocolate chips. This would simply mean that 1,475 is P 96.44, because the area below that is 96.44, which we can approximate and write it as P 96. But the accurate answer is P 96.44. So I guess I'll do part E right here. Or part F, I mean, I'm sorry. So 1,262 is right there, and 1,050 perhaps right over there. So the area below 1,050 has to be definitely less than 50%. So the rank the percentile rank of 1050 must be below 50. So we first find this area. The starting value is negative E99. The ending value or the upper value is 1050. The mean is 1262. The standard deviation is 118. I put that all in. I end up getting an area of 0.0362. So 3.62% is below P50, below 1050. So this number, 1050, would be P3.62. If you want to round, you can call it as P4. So that's how we find percentile ranks. So here is a problem on Wendy's drive-through. So all fast food restaurants do analysis, statistical analysis, using the data to train their employees to make profit and so forth. So the faster a car would go through a drive-through, the more money the company is going to make. It is given in this problem that Wendy's had found that the mean time that a person would spend in a drive-through is 138.5 seconds. They want us to make an assumption that the standard deviation is about 29 seconds. And we have to find the following probabilities. So key things to note here is the time is normally distributed. The mean is 138.5. Standard deviation is 29. I am going to call T to be the time spent at the drive-through. So part A would like to know, or would like us to find the probability that the time is less than 100 seconds. So the mean is 138.5. The standard deviation is 29. So the answer definitely has to be below 50%, because 100 is somewhere down there. So that area is going to be below 50%. We will say about 8% this time. That is going to be my guess. There's nothing wrong in being wrong, so we will see. So the area starts at negative E99, ends at 100. The mean is 138.5, and the standard deviation is 29. Enter. 9%, I was very close. So the value here is 0.092. It's 157, we can call it 16. So 9.2% of the cars will spend less than 100 seconds at a Wendy's drive-through. I will certainly disagree with that when it comes to my neighborhood Wendy's. So part B, would want to know the probability that a randomly selected car would spend more than 160 seconds in Wendy's drive-through. So more than $160 would simply mean it's somewhere right over there. And we are trying to find the area above that 160. So it is going to be between the first and the second standard deviation based on the picture. So I am going to sort of guess, and I'll say 11%. Let's see if I'm going to do well. So second bars start at 160, end at E99. Mean is 138.5. Standard deviation is 29. It's actually 22%. So the probability that T is greater than 160 is 22.92% or 0.2292. Now they want to know what proportion of cars spend between 2 and 3 minutes in Wendy's drive-through. It is very, very important to keep in mind of the unit. The problem talks about the time in seconds. And here we have the information in minutes. So the first thing that we have to do is to convert it to seconds. 2 minutes would be 120 seconds. 3 minutes would be 180 seconds. So part C would want to know the probability that the time is between 120 seconds all the way up to 160. So what we're trying to do is we're trying to find that area maybe about 30% or 40%, we will see. So 120 less than T less than 160. So second bars, the area starts at 120, ends at 160. The mean is 138.5. The standard deviation is 29. 50%. So there is a 50% chance that a car would spend somewhere between 120 and 160 seconds. In other words, 2 minutes and between 2 and 3 minutes. And lastly, part D, would it be unusual for a car to spend more than 3 minutes? How do we determine if something is unusual or not? We find the probability of the event happening. So first, I'm going to find the probability that the time is going to be greater than 180 seconds, which would be 3 minutes. And we're trying to find that area. It is likely to be small. So the lower endpoint is 180. The upper endpoint is E99. The mean is 138.5. The standard deviation is 29. And, oops. Ooh. 0.0762. So that the time t spent by a car at the Wendy's drive-through being greater than 0.0762 and its probability, greater than 180, and its probability is 0.0762 or 7.62%. Now, it is kind of subjective for us to call what unusual is. Now, there is a difference between a rare event and an unusual event. Unusual is something that doesn't typically happen. So would I consider this to be an unusual event? Yes. Would this be a rare event? No, because a rare event will happen at a probability less than 1%. That's what we call rare, even less than 0.5%. So it's a very, very small probability. But this, is it unusual? Yes, because the probability that a person would spend more than 180 seconds is about 7.62%, which sort of makes sense. So my neighborhood Wendy's is definitely unusual. So egg incubation times. The mean incubation time of fertilized eggs kept at 100.5 degrees Fahrenheit in an incubator is 21 days. And it is said that the times are normally distributed, has a standard deviation of 1 day. So we know the mean, we know the standard deviation, and above all, the data is normally distributed. So mean, 21, standard deviation, 1 day. The empirical rule is sort of easy in this problem because the standard deviation, we don't have to do a lot of work. So let me make this bigger. So 21, add 1, we get 22, 23, and 24. 20, 19, 18. One standard deviation to the right, 2 to the right, 3 standard deviations to the right would be 24. I am doing the same on the left-hand side, -1, 20, -2, 19, -3, 18. The reason why I did this is because I know what their corresponding percentiles are, the empirical rule. This is in the previous video. So what are the percentiles? This is P.15, P2.5, P16, P50, P84, P97.5, P99.85. So I know the percentiles already. Now, what they want to know is they want to determine the 7th percentile for incubation times. Mind you, in the problem that we did earlier, we wanted to find the percentile rank in part E and part F. Here, we're not finding the percentile rank, Rather, we want to find the time corresponding to the percentile rank. The percentile is given to us, 17th percentile. What is the time? Well, if I look at this picture, I can see P16 and P15. Because of the nature of the curve, P17 is likely to be right there. And very small change between 20 and 21. So I am going to guess it would be about 20.1 or 20.2 days. We will see if that is true. So in this case, since we are finding time corresponding to the 17th percentile, which is P sub 17, that's what we need to find. So this would mean 17% of times will be below P17. So let's go back to the calculator. We shouldn't use Normalcdf because we're not trying to find the probability. We're not trying to find the proportion. We're not trying to find the percentile rank. Instead, the percentage is given to us and we want to find the time. So the area below is 0.17. The mean is 20. The standard deviation is 1. Put them all in, I get 19.04. So for a second, I thought, there is no way, I must have made a mistake somewhere. I put 20 instead of 21, I'm sorry. So 0.17, mean is 21, standard deviation is 1, and enter, 20.04. So P17 is 20.04. As you can see, the dash that I put earlier in magenta is very close to 20. Part B, we have to determine the incubation times that make up the middle 95% of fertilized eggs. So middle 95%, let me pause this for a second. So middle 95% would simply mean whatever that we have right in the middle. So 2.5 is right here, and 97.5 is right there. So 19 days would correspond to P2.5. And P97.5 is 23. So the times that make up the middle 95% of fertilized chicken eggs is the times that are between 19 days and 23 days. And why is that so? Because 97.5 minus 2.5 will give us 95%. So here is another problem that is on reading rates. The reading speed of 6th grade students is approximately normal. First thing to note, the mean is 125 words per minute. Standard deviation, 24 words per minute. And we want to find the rating speed of a sixth grader who's reading, we want to find the reading speed of a sixth grader whose reading speed is at the 90th percentile. So what is given to us? We are given that the reading speed is going to be at the 90th percentile, and our objective is to find that speed. So (125), let's go ahead and use the empirical rule and add the standard deviation so we can do guesswork. So 125, 149, 173, 197. And on the other side, we have 101. And we have to subtract another standard deviation that would put us at 77. Subtract 24 from 77, 53. And what are their corresponding percentiles? So that is P50 right in the middle, P.15, P2.5, P16, P84, P97.5, and P99.85. And those are the percentiles. We want to find the reading speed corresponding to the 90th percentile, which would simply mean it has to lie somewhere right there. So because P84 is 149, P97.5 is 173. So P90 has to lie between those two percentiles, which would correspond to the reading speeds 149 and 173. So the answer has to be a number definitely between 149 and 173. So how do we find that probability? So we want to find the area below, and we want that area to be 90%. So second verse, number 3, the area below is 90%. The mean is 125. The standard deviation is 24. 155.75. So part A, the reading speed is 155.75 words per minute. Now, part B, a school psychologist wants to determine reading rates for unusual students, both slow and fast. Determine the reading rates of the middle 95% of all sixth grade students. What are the cutoff points for unusual readers? So we're going to say anything that is above 97.5, the 97.5th percentile, and below the 2.5 percentile to be unusual. So that area would correspond to the middle. %. So, oh, I have to go a little further. Right there. So P2.5 is 77 words per minute, and P97.5 is 173 words per minute. So what would be unusual? Well, anyone who reads below 77, sixth grader who reads below 77 words per minute would be considered as a slow reader. Any sixth grader who reads above 173 words per minute would be a fast reader. Because the middle 70 95%, the regular people are between 77 words per minute and 173 words per minute. Not saying that, you know, if you're below 77 and about 173, you're becoming irregular. What I meant to say was the normal values that fit the profile.